All right. Good evening, everyone. Welcome back to Math 261, our third meeting together. Still throws me off. I feel like it should be our fourth, but it's our third since we had that holiday. Reminder that 1.1, 1.2, and 1.3 homeworks are due tonight by 11:59 p.m. So hopefully you've got the majority of those done by now. If not, you will have a couple hours after class. And then we are going to finish 1.4 and 1.5 today. We will complete those completely. So those are going to be due in a week by 11:59 p.m. Remember, the due time is always going to be 11:59 p.m. for a date. And generally, homeworks are always going to be due the following Monday, unless there's some weird exception. I still don't have a test date for you because it's going to be at least several weeks. It's definitely not going to be next week, and it's not going to be the week after that. It might be the week after that, but it might even be one more after that. So yeah, just this first chapter, we've got more sections to cover than the rest of the tests. So it just takes us a lot longer to kind of get things in gear and ready for that first test. What else did I want to say? We will begin 1.6 tonight, but we won't get very far. I think we're going to get about 2 examples into that, but we have obviously got some time before then. So let's go ahead and pick up where we left off doing derivatives. With that example I showed you the problem for C last time, but now we're going to actually get into it. So as always, if you have any questions, I'll be in the chat. This video is not going to be very long. We only have like 14-15 minutes left of this one, and then I'll put it into the next one, and then we'll have our break after about an hour and 20 minutes total. So f of x is equal to 1 over x, and let's do this at an x value four. We don't know the derivative of this function yet. We never found it. So we have to do that whole limiting process for this one. So first, find f prime of x. This is a significantly longer problem for multiple reasons. So f prime of x is the limit as h goes to 0. I'll write the definition one last time of f of x plus h minus f of x all over h. So that would be the limit as h goes to 0. Now f of x plus h, this x is in the bottom, so it's 1 over, and the x turns into an x plus h. This right here is the f of x plus h. Then the minus, f of x is the original function, 1 over x. Then the bottom of the main fraction is h. This is what we call a compound, or some people would call it a complex fraction, because it's a fraction inside of a fraction. It's inception. We don't like that. We don't like that. We can't have that. We need to clean this up. To do that, what we have to do is find an LCD. And then there's multiple methods for this. You can find the LCD of all the fractions and multiply that out, or you can do it a slightly different way of the top. So I'm only looking at the tops. I'm ignoring this h in the bottom since it's not a fraction. So just the x plus h and the x. Well, that LCD is x times x plus h. They're completely different. So you have to have them as a product. And then we will multiply each fraction, top and bottom, by what it's missing. So multiply top and bottom. FedEx is here. Multiply, and now my dogs are going to start going nuts. Sorry. Multiply top and bottom by what's missing. This guy and this guy. We're leaving the h alone. So equals the limit as h goes to 0. I am leaving the h alone in the bottom. The 1 over x plus h needs to multiply top and bottom by h. That's the missing factor from the LCD. That's how we get LCDs. That's the more normalized way of doing things. LCD is the product of everything, x plus h and h. So that was the first one. Then for the second one, minus, here's our 1 over x. So it has the x, but not the x plus h. And I did these as h's. I got distracted by everything going on. Those are supposed to be x's. The LCD was this thing, x times x plus h. So they're supposed to be x's. X, x. Sorry about that. The second fraction has the x in the bottom, but not the x plus h. So we multiply top and bottom by x plus h. I'm also going to do something extra. The h in the bottom, I'm going to write it over 1. That way, we have something special in a minute or two. So equals the limit as h goes to 0. This first fraction is now x over x times x plus h. Hold on for a second. Minus the second fraction, the x plus h times 1 is x plus h in the top. The bottom is the LCD, x times x plus h. Then all over h over 1. Now in the top portion of the fraction, I'm just looking here. These now have a common denominator, so we can combine them. So we're going to combine the top fractions, f's fractions. So this is equal to the limit as h goes to 0. Now that's a minus and multiple terms, so you got to have parentheses. X minus parentheses x plus h all over its common denominator of x times x plus h. See, that's the same, so we only need to write the denominator once now that I'm combining the fractions. Then all over the h over 1. Distribute. So that's x minus h all over x times x plus h, then all over h over 1. The x minus the x is going to cancel. So on the top we have just a negative h. So this is the limit as h goes to 0 of negative h over x times x plus h. Then that's all over h over 1. Note, a over b over c over d is the same thing as a over b division symbol c over d, which is the same thing as a over b times d over c. I'm going to use that to fix this. So it's no longer fraction divided by fraction. So now, this is the limit as h goes to 0 of negative h over x times x plus h. We're almost there. Times 1 over h. Again, the h over 1, we were dividing by h over 1. That's the same as multiplying by 1 over h. We're only able to do this once it's a fraction divided by another fraction. With all these pluses and minuses, we couldn't have done that before. With the separated fractions, we couldn't have done that before. So we still have that h in the bottom. We said generally that's what we want to see cancel. Well, now there's an h in just the top, there's an h in just the bottom. They cancel. So what we get is the limit as h goes to 0 of negative 1, don't forget the negative, that's a common mistake, over x times x plus h. Now you might say, Mr. Beckner, there's still an h in the bottom, but it's not just an h. It's an x plus h, and that makes a difference. Now let h be 0. So we get equals, no more limit, negative 1 over x times x plus 0, which is negative 1 over x times x, which is negative 1 over x squared. So the derivative, finally, is negative 1 over x squared. If this was a calculus class, we'd be doing a lot more like this and even more complicated. If this was a regular calculus class, this is an applied calculus class, so that's about as difficult as I go. I want you to ignore any that have a square root in the homework for now. For now, using the limit process, ignore square roots for now. It uses a technique that I don't really think we need in an applied business calculus class. So this is about as nasty as it gets using limits for now. This was a more complicated process, but you've seen it in the notes, which means you could see it in the homework, which means you could see it on a test. You might not. You might, or you might not. I said might a lot there, didn't I? That was weird. It's weird how I said you might more than I didn't. I wonder what that means. Okay. So anything you've seen here is good testing material. Like I said, the homework sometimes gets a little more complicated. I don't test on the more complicated stuff. I leave it there in the homework so you can see it, so you can try it. But the tests I keep more similar to the notes, just so you know. We're not done. All we've done is found the derivative. The whole point of this problem was to find a tangent line at x equals 4. So we've only done the first bit, but thankfully that was the worst of it. Now that we have our derivative, we can go and find the point, the slope, and jam that information into our equation, which we can finish in the time we have left. So again, f of x was 1 over x. F prime of x was the 1 over x squared. And we were supposed to do this at x equals 4. So to find our point, we do f of 4, which is 1 over 4. So the point is 4, 1/4. This is the reciprocal function, so the input is just flipped to get the output. F prime of 4, this will give us our slope at that point. That's negative 1 over 4 squared, which is negative 1 over 16. So that's our m. The only information we need now is those two numbers in this number, the point and the slope. And we put those numbers, that information into y minus y1 equals m times x minus x1, and we solve it for y ultimately. So y minus y1 is y minus 1/4 equals m, which is negative 1/16 times, parentheses, x minus x1, which is x minus 4. Clean it up. Distributing the negative 1/16 will give us y minus 1/4 equals negative 1/16 x. Negative 1/16 times negative 4 is negative 4 over 1. The 4 and the 16 would reduce to a 1 and a 4. The negatives would cancel to positives, and you end up with positive 1/4. You better know how to clean up your fractions. So that's a plus 1/4. So y minus 1/4 equals negative 1/16 x plus 1/4. The 1 in the top, you could just write that as x over 16 as well. If you then add 1/4 to both sides, you better know how to add your fractions as well. No excuses. We get y equals, let me just write it over here, negative 1/16 x plus 2/4, which is negative 1/16 x plus 1/2. And that is our tangent line, but only at x equals 4. If you want to do it at x equals 3, you got to plug 3 into the function, which would be 1/3, plug it into the derivative, which would be negative 1/9, and then do the same equation. I don't ever have equations of tangent lines for a function that's a line because it's literally the line. This process is only done for curves. Things like x squared, x cubed, 1 over x, in theory, square root of x. But like I said, we'll focus on that idea later with a simpler equation. So that is where we're going to leave today at. I believe we have finished 1.3 and 1.4. There's just a couple very, very basic ideas that we need to discuss. Yeah, we'll say 1.4 is almost finished. We'll spend maybe 10 minutes doing one more example using the limit definition, and it'll be with a multiple term polynomial. I'll even say it out loud. It'll be x squared minus 5x plus 12. That'll be the first thing we do next class. Then we'll give you an alternate notation to the f prime of x, and then we'll talk about what it means to be differentiable and how some functions aren't differentiable at certain points, but they are at other points. And obviously we're going to be doing that right now. We're not done for the day. So hold tight while I set up that next video. Example, I honestly don't remember where we're up to. I have example 5 on my notes, but I think I did an extra one or cut one. So example number question mark doesn't technically matter. And we're going to find f prime of x, which is the derivative if f of x is equal to x squared minus 5x plus 12. So this will be the last one where we do a limit to find a derivative. And then we'll have one small topic to close out the section with, and then we'll get into formulas that'll help us knock these out a lot quicker. So remember that f prime of x, the definition of that, f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. You have to have that memorized for this chapter and then for the final exam. Admittedly, we won't use it in chapter 2, 3, 4, but it's not something I want you to forget, especially since if you forget in chapter 2 and 3, by the time you get to final, you got to relearn it. That's more of a pain than having to just remember it constantly. I'm going to first, in the interest of this problem, write out f prime of x equals the limit as h goes to 0. So for f of x plus h, I don't know if you can hear my dog scratching or not, but he's really getting it right now. It's okay, buddy. He's got allergies and it's a rough time of the year. All right, so the limit is h goes to 0. We got the f of x plus h. Sorry for my distraction. So come on, buddy. Stop it or I'm gonna make you move. The problem is I can't, he's sitting under my table kicking me, so I can't really work right now. This is fun. All right, so f of x plus h, that's where we're turning these x's into x plus h's. So I'll show that with color. And it looks like my marker is defaulting back to black like it should. So that's nice. Let's see how long that takes to fail. So we'll go x plus h squared, then minus 5 times x plus h plus 12. And I'll show the x plus h's in red. So this right here, all I've written so far is just the f of x plus h. Then we have the minus f of x, minus, and because there's multiple terms, you need a parentheses, x squared minus the 5x plus 12, then all over h. Remember, this was just originally the slope formula, y2 minus y1 over x2 minus x1. But then we changed it to function notation, f of x2 minus f of x1 over x2 minus x1. And then we called x2 just the original x value plus h. And when we did that, the x's in the bottom canceled. That's why it doesn't quite look the same, but arithmetically and algebraically, it is the same. Now we have a parentheses squared. This is like the 3rd or 4th time we've done this together, so we need to simplify that. So f prime of x is the limit as h goes to 0 Sorry, more stuff with my dog. So parentheses, we're going to have to write that times itself. So that's x plus h times x plus h. I am going to skip writing that step right out here. X plus h times x plus h. That's x squared plus xh plus xh plus h squared. If you don't know how I got that, go back to last lecture, and it may have actually been the lecture as well before. May have seen the last two lectures, but that x plus h squared is x plus h times x plus h, and then you FOIL it, and you'll get those 4 terms. Then we can distribute the minus 5, so that's going to be a minus 5x minus 5h. Watch your signs when you distribute negatives. Then the plus 12. Then we're going to distribute this negative to those 3 terms. That's minus x squared plus 5x minus 12. Then all divided by h. Now, what happens here is lots of stuff, in fact. So this will be equal to the limit as h goes to 0. We get lots of terms that will cancel. The xh and the xh, here and here, these 2 terms are going to stack. They're going to make a 2xh. But this x squared with this x squared that's minus, those 2 terms are going to cancel. X squared minus x squared, gone. So they're gone. This one's gone, this one's gone. We also have this negative 5x and this positive 5x, gone, gone. Then we have this positive 12 and this negative 12, gone and gone. 6 of the terms are gone. The only things we're left with are the terms that have h's. This is pretty common. So we got the xh plus the xh. There's 2 of them, so that's why it's 2xh. Then plus the h squared. Then there's this minus 5h kind of in the middle of everything. And then that's all going to be divided by the h. And I've said that you can then factor the h out of the top and cancel it with the one in the bottom. Whether you share that factoring work or not is up to you. I'm going to just reduce it like I did last time. So there's an h in all terms, so I can get rid of a single h in all terms. So this h is gone, this h is gone, this h is gone, and this h squared will turn into h to the first. So this is now the limit. As h goes to 0, the first term just has the 2x, then it's a plus h, then it's a minus 5. There's no more bottom, there's no more h in the bottom, which means we are now no longer in the indeterminate form. We can actually go and plug this stuff in. We can plug the h in, that is to say. So now we plug in. If you had done it at any point before, you would have got 0 over 0, the indeterminate form. So this is 2 times x, the x stays, plus the h we said is going to become 0. Please stop kicking me, buddy. And then the minus 5 stays, which is just 2x minus 5. So that says the derivative, in other words, the function that dictates the slope of the original function is 2x minus 5. So what that means is, if I have a particular x value I want to know the slope of this curve at, because its slope changes constantly, if I want to know what happens at x equals 1, what's its slope? 2 times 1 is 2, minus 5 is negative 3. Its slope is negative 3. If I want to know what happens at 10, 2 times 10 is 20, minus 5 is 15, so its slope is 15 at x equals 10. If I want to know what happens at 100, you get the idea. You can do this for any x value. Stop it, stop it, stop it, stop it. Come on, Rambo. So up to this point, we had only done this for single term higher order polynomials, or we did it with a binomial that was linear. We hadn't done it for a trinomial, and the idea is really just that this x squared bit ends up leading to the 2x, and this minus 5x bit ends up leading to the minus 5. Separations of pluses and minuses really don't have an effect on derivatives ultimately when it's just pluses and minuses. Now when you throw products and quotients in there, that changes the game severely, but we'll get to this. We're building to a point. But if you remember, when we did just the derivative of x squared, we got 2x. So this x squared and this 2x are related to each other. If, let's just say, I'm going to highlight this for a second and then get rid of it. Let's just say this was the function. Say the x squared wasn't there. That would be a line. Lines have slopes of whatever's in front of x as long as it's a function. So the slope would be -5, and look at that. That's a -5. It's not a coincidence. Those are related to each other. Okay. So there is another notation for derivatives. Derivatives means differentiation. It means finding a rate of change, finding a slope of a function. All of these are the same thing. So the notation looks like this. This is the notation we had at first. This was kind of our function notation for derivatives. The other one looks like this. Little df, then on top of little dx. You don't usually say the littles. df dx is how you would say this. df dx. So this is, all right, hold on, I'm gonna mute for a second. I love my dog, but he was complicating things too much. All right, so where was I? This f prime of x, that's how you would read that one, is the same as saying df dx, df, and I'm gonna put a little dash, but you don't say the dash, dx. I'm just saying df dx. Or in a more sentence-like version of it, the derivative of f with respect to x. And that with respect to idea, that's something you're going to hear constantly throughout the semester. What the with respect to means that that's the independent variable. That's the variable that we are studying the change of. So how y changes with respect to x. So as x changes, what happens to y? So that's what's happening here. So with respect to relates to the independent variable. And it's not always x. We can have functions of multiple variables. So we could take the derivative with respect to x, or we could take it with respect to y, with respect to z, or what other letters we have up there. But the d's, we use d's for derivatives. And now this looks like a fraction, doesn't it? df over dx. Oh, cancel the d's. Do not. This looks like a fraction that you could cancel the d's on. Do not, do not, do not, do not, do not do that. This is something much more complicated, even though quite often we consider this as a fraction. It's not really a fraction, but a lot of the operations we can do with it act like it's a fraction. Because it is a fraction in that df is a thing and dx is a thing, and we are studying the change of those. It's how the function changes with respect to how the independent variable changes. But the d's are not their own thing. The df is a thing, the dx is a thing. So how can we use this notation? Let's say our f of x was equal to x cubed. F prime of x, in other words, the derivative of the function, this would be the same thing as taking the derivative with respect to x of x cubed. This notation is the same as saying do this thing. So when you write d over dx, that says to take the derivative of something with respect to x. So x cubed is our function, so here's the function. And then we're taking the derivative of that. So this right here is what tells us to take a derivative if we don't use the prime notation. And yes, it is the same thing as df dx, but it's just another way of actually writing that, because you'll see us write things this way, you'll see us write things this way, we're going to see things written this way. We write it all the different ways. Now this new notation is named after its creator, who was Leibniz, Leibniz. So if this was like a regular high school calculus class, or normal Calc 1 class, we would actually study a little bit of history of calculus. And there were two dudes, two cool dudes of the 1800s that basically came up with calculus at the same time. There were arguments that one stole from the other. It got pretty nasty. Maybe there was, maybe there wasn't. That's what I not really want to get into. But those two people were Isaac Newton and Leibniz. And I'm blanking on the dude's other half of his name. Gottfried Wilhelm Leibniz, and that's why no one ever refers to that guy by Gottfried Wilhelm, just Leibniz. Newton is a much more popular person, so most people know Isaac Newton. So Newton had his notation, Leibniz had his notation, and they were both good, so we use both of them. There are times when that prime notation, which was Newton's, is better. There are times when Leibniz's notation is better, when we kind of want to think about these from a slightly different angle, so to say. So we will be using both. You'll see both constantly and frequently. All right, the final topic of this section, and this is on differentiability. In other words, whether a function has a derivative, whether it has a derivative everywhere or just some locations. So a function is differentiable if you can find the derivative of x, and it's valid everywhere. Generally, a function is not differentiable at a point if it is not continuous. Some people would say discontinuous. Or if it is not smooth. What does smooth, actually, let's say, what does not smooth mean? Not smooth means, again, in general, it's a corner. So this is a smooth curve. It bends, it ebbs, it flows. This is differentiable everywhere. This is smooth and differentiable. I'm just going to abbreviate it with diff, not difference, differentiable. This is not smooth. Kind of looks like a W. There are three particular points here, here, and here that look like corners. It's an absolutely sudden change. It's going down, and then at the snap of a finger, without any warning, it just completely changes the direction, kind of like the stock market can do sometimes. So this is not smooth because of the corners, because of the jerking action happening at those three dots, and thus not differentiable at the three dots. It's differentiable in the other sections. You could, this is a piecewise function, and you could say it's differentiable everywhere except here, here, and here. So you can actually find derivatives of those four different sections, but you can't say that it's valid at the three red dots. Because on the left, the slope is like a negative, let's say -1, but on the right of it, it's +1. It's kind of like when the limit is different. So when the limit is different, we said that the limit doesn't exist. This is the slopes being different. So it's kind of like the slope doesn't exist at the singular point. Is it 1 or is it -1? It can't be both. It has to be one or the other. That's why we say it's not differentiable, because its slope has just, in the snap of a finger, changed from one thing to another. Whereas on the left one, you know, it starts out, maybe it's +1, then a half, then a quarter, then 0, then a -quarter, a -1/2, a -1. It's changing smoothly. It's not just a sudden, oh, it's going from 1 to -1 at the drop of a pen. So you'll find a couple questions about that in your homework. Hey, is it differentiable at these 4 or 5 points? Or is it, you know, which of the 4 or 5 points is it differentiable? Which ones is it not? Or can you just tell the points? But that's the idea. and this is a fascinating concept that, again, in a regular calculus class, we would study a little more extensively. But in here, it's more of just kind of a quick discussion, and still an important idea. I could still test on this. You have homework on it. But we just don't study differentiability as extensively in here, because we don't need to know the kind of long-term effects of it. But that is 1.4. So 1.5. The power and some rules, some difference rules. Of differentiation. Slightly different title than what it says in the book. The book actually throws the Leibniz notation in the title as well, but I like to discuss it in 1.4 because it just feels appropriate to do before differentiation. All right, so back in 1.4, we used the definition of the derivative, which was the limit as h goes to 0, all that stuff, of the f of x plus h minus f of x over h. And we saw that algebraically, you know, some of them weren't the end of the world, some of them were a pain in the butt, and we honestly didn't even do that many in terms of how complicated they can be. We didn't do any with square roots. Those can kind of suck. We didn't do any with higher order powers and denominators. Those can kind of suck. We didn't do anything with higher order powers than a 3 and from a numerator, because those can kind of suck. The algebra just gets worse and worse and worse the bigger an exponent is. When you start throwing square roots in there, it gets crazy. When you start throwing absolute values in there, it gets kind of weird because you need to approach it as a piecewise function. But we're going to need to be able to do this stuff just bam, 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 quickly, quickly, quickly. In the time that it took us to do one problem, we should be in the last section with the limit, we should be able to knock out 5, 6, or 7 of those. Well, how do we do that? We can't do that with that intensive algebra every time. Well, thankfully, there are formulas for finding derivatives quicker. These can be derived. We will not derive hardly any of them. If any of them, it's just going to be more of a kind of look at a pattern and see what you can take away from this. So before when f of x, and we had a number in front of it, I'm just going to ignore the number. If your function is a line, we know the slope is the number in front of it. So there's a 1 implied here. So if your function is x, the derivative by going through that limiting process would be 1. And again, you know that's true because the slope of a line is the coefficient of x. When we did the function x squared, we found that its derivative was 2x. When we did the function x cubed, we found that its derivative, f prime of x, was 3x squared. Now, we did not do this one, but we'll pretend that we did. If we did x to the 4th, so you'd have an x plus h that you're multiplying out 4 times, which makes it 1 layer of difficulty more difficult than x cubed. It turns out that its derivative And feel free to demonstrate this on your own. It's similar to the x cubed, again, with just one more extra complicated product to do in the process. It's going to end up being 4x cubed. So in an advanced calculus class, in an honors advanced calculus class, what we can kind of do is keep doing this and keep doing this and keep doing this. And we can ultimately just generate this for an x to the n. So you can say if your function is x to the n, what does the derivative end up being? And it's some complicated algebra that we're not going to do. So instead, what we're going to do is pattern recognition. And the first one's not super great for it, but the others are. So x squared, the exponent was a 2. Look at the derivative. The 2 is now a coefficient. And look at the exponent. It's now a 1. It went from 2 to 1. All right. When your function was x cubed, it was a 3 as your exponent. Look at the derivative. There's a 3 out front. So it seems like the exponent ends up becoming a coefficient. When the exponent's a 2, the coefficient's 2. When the exponent's a 3, the coefficient becomes a 3. When the exponent's a 4, the coefficient becomes a 4. So our derivative, it just seems like we take the exponent and make it the number out front. Well, what about the exponent? What happens to that? When it was a 2, it becomes a 1. When it was a 3, it becomes a 2. When it was a 4, it's going to become a 3. If it was a 10, it's going to become a 9. So the exponent seems to be dropping by 1 each time. So what this does for us is it gives us our formula. So the power rule states that if your function is just an x to some exponent, so n is a number, 2, 3, 9, whatever, 1, 0 even, then f prime of x is equal to n times x to the n minus 1. So we take whatever the exponent was, we make it a coefficient, and then we take what the exponent was, which is n, and we drop it by 1. If you prefer the other notation, if you want to write df dx, then it's n times x to the n minus 1. The formula doesn't change. This is the power rule of differentiation. You will use this without exaggeration 500 to 1,000 times this semester. That's not exaggeration. If you don't learn this rule right now, you will fail this class. You cannot pass this class without the power rule. There's absolutely no way. You will use it over and over and over and over and over and over and over. Now, we will learn several other rules as well, and they will all be important, and they will be, I don't want to say as equally important, but they are important. They will get used, dozens of times. This one gets used hundreds of times. These other rules that we'll be learning, when you're using those rules, you'll be using the power rule inside of those other rules. So you have got to make sure that you memorize this and that you understand how to use it. Now, I want to give a couple of kind of special cases here. These are special cases because the power rule still applies. Let's say your function is just a constant. If your function is just a constant, so let's go with C. Actually, let's go with A, because I'm going to use the A later as well. So if your function is a constant, C or A, whatever letter you like, then the derivative is 0. Or you could say the derivative of, so d dx of A is equal to 0. You technically don't need the parentheses around the A. I'm just being thorough. So again, the two different notations both saying the same thing. So if your function is a constant, 7, 9, a half, pi, negative a million, the derivative is 0. The reason is constants are horizontal lines. Horizontal lines have a slope of 0, so the derivative is 0. Horizontal lines have a slope of 0 everywhere, so the derivative is 0 everywhere. Now you might say, well, how does this come about from the power rule? Well, if there's no x's here, so it's like having, I'm going to write something that I'm going to erase. Let's say this is really f of x equals a is the same thing as having a times x to the 0. These are the same thing. A is a x to the 0. Because anything to the 0 is 1, so this really isn't even here. So f prime of x, you'd bring the 0 out front, and 0 times anything is 0. So the derivative of a constant is 0. The derivative of a constant is 0. The derivative of a constant is 0. Another case, if f of x is equal to ax, a times x, then the derivative, well, this is a linear function, a times x, so the derivative is the slope. The slope of that line is a. And if you don't trust that with the power rule, here's the explanation. I said I was going to erase it, I won't. If your function is a times x, then f prime of x, there's a little 1 that's implied to be there, so the 1 goes in front, times the a. Now, I'm not explaining why you can leave the a there yet, just go with it for a minute. Then you're going to drop the exponent by 1, so that's x to the 0, and x to the 0 is 1, so that's 1 times a, which is what? Which is a. So it's nice to know these two special cases off the cuff. You can still apply the power rule every single time, but you will see them hundreds of times. So I suggest that you know the derivative of a constant is 0, and the derivative of a linear term is the coefficient. Extremely helpful to know. All right, so let's start doing some official examples now. Example, was that a question? No, it's just someone, I think someone emailed me. Example 1. Find f prime of x, aka df dx. So for A, let me make sure I got plenty of space. Good for now. F of x equals x squared. Every single one of you by now should know that this is 2x. We did this with the limiting process where we did the x plus h squared and all that algebra jazz. Now we're going to take our shortcut. Now remember, on a test, if it says to use the definition, you have to do it with the limits. I did not say by the definition, so I'm taking a shortcut, baby. So f prime of x, we're just going to apply that formula, which was up here. You take the exponent and you make it a coefficient. You bring it out front as a coefficient. You're still going to have your x, and then you drop the exponent by 1. That's what n minus 1 means. Just take the original exponent and subtract 1. So I'll show all the detailed work here. So the 2 comes out front. So this 2 comes out front. Then we leave our x, and its exponent should be, we take the original exponent of 2, and we drop it by 1. So this is 2 times x to the first. No one ever writes an exponent of 1 in an answer, though. So that says f prime of x is 2x, the same thing that we got previously. Or if you want the new notation, df dx is 2x. Those are the same thing, just different notations. Tomato, tomato. That was so much quicker than having to do x plus h times x plus h is x squared plus xh plus xh plus h squared, then combine those like terms, which will give you your 2xh in the middle. The x squared would cancel with a minus x squared at the end. You cancel your factors of h, then you plug in the h equals 0. And as quick as I can say it, it takes us a lot longer to write it and do it. Dropping an exponent and then subtracting 1 from it, wow. Wow, it's so much faster. Memorize that rule yesterday. Obviously, I'm exaggerating with the yesterday part. You get what I mean by that. All right, let's do many more. F of x equals x cubed. So we know from last lecture the answer to this is 3x squared. I even pointed it out earlier. And this one was a bigger pain in the butt than the x squared because you have an x plus h times an x plus h times an x plus h, which gave us something like x cubed plus 3x squared h plus 3xh squared plus h cubed, and then you end up canceling an x cubed term. You factor out an h, you plug your h equals 0 after canceling the h, and you got that, 3x squared. Whew, it's a lot of work just talking about it, right? It's a lot of work just listening to me talk about it. Well, let's try this formula, f prime of x. I'm going to skip writing so every single time. Take the exponent, which was a 3, make it a coefficient. Leave the x there, but drop the exponent by 1. So take the 3 and subtract 1. 3 minus 1 is 2, so you get 3x squared. Holy cow, that was fast. I don't want to box it up like that. I want to box it up with the notation. So f prime of x is 3x squared. Or df dx is 3x squared. Again, same exact meaning. It's just sometimes we need to think about it as the right version. We're saving that idea for much later, don't worry. Just getting used to the fact that there's 2 ways to write it for now. C. I'm not going to do this officially, but if I had x to the 4th, you'd bring the 4 out front, drop the exponent by 1, and you'd get 4x cubed. That is so much faster than doing an x plus h times itself 4 times, foiling, then multiplying, then multiplying, and then multiplying all sorts of crazy terms and getting an answer that I don't know off the top of my head. It's like a x to the 4th plus 1 x h cubed plus 4, no, plus 6. I don't remember. I'm not going to do that in my head. But the point is, you don't need to. If you had an x to the 100th, in fact, I'm going to throw an extra c in here. This was not my official c, but x to the 100th. Good Lord, that problem might take you hours to do with the definition. But with this power rule, f prime of x, bring the 100 out front. Take the x, drop its exponent by 1. See how much quicker it is when I don't have to mess with that blue to black. And you get 100 times x to the 99th. Took me like 10 seconds. I'm going to skip writing the other notation this time. D. F of x equals 1 over x to the 4th. Uh-oh, rationals, fractions with variables and bottoms. Run away, scream, cry. No, we got this. The power rule is in a very specific format. Let's go back up here. If your function is written as x to the n, that doesn't say 1 over x to the n. That doesn't say 20 over x to the n. That says x to the n. In other words, the x has to be in the top. This x is not in the top. It's in the bottom. But we have a technique using exponent rules, which are in Canvas as reminders if you don't remember them. There's a technique to bring variables from top to bottom or bottom to top as long as there aren't extra pluses or minuses, extra terms littered everywhere. So what we can do is bring the x to the top. So our function is now going to be 1 times, I'm leaving the 1 in the top, x to the, what happens when you move a variable from top to bottom or vice versa? Its exponent sign changes. So that's now a -4. So f of x is just equal to x to the -4. I don't need to write that 1 in the front. We're going to get into what it means if there's an extra coefficient. So if there's like a 2x to the -4 or a 5x to the 7th, something like that. Honestly, it's a super easy fix. So now we're ready to apply our power rule. So scroll up again, just in case. What do? We take the exponent, we bring it out front, then we drop the exponent by 1. For the love of math, watch your signed arithmetic. You have got to know how to subtract negatives. No excuse at this level. I do not like calculators being used for the first test of this course. I like calculators for like test 3 and for the final and sometimes test 2, but I generally give no calculator tests for test 1. So I'll write the so since it's down here. F prime of x. What do? We take the exponent, which is the -4, include its sign. We bring it out front. There's a -4 out front. We leave the variable, but we drop the variable by 1. Now, a lot of people just instinctively say -3, because before the 100 went to a 99, the 3 went to a 2, the 4 goes down to a 3, a 7 goes down to a 6. So a -4 goes down to a -3, and that's wrong, 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 wrong. Admittedly, I've done that once or twice. But remember, subtraction with negatives works differently. So this is -4 minus 1. Which leaves the -4 in front, and the x, -4 minus 1 is not -3, it's -5. Same sign, add the numbers, keep the sign. Different sign, subtract, keep the sign of the larger. That's your rules for adding and subtracting sign numbers. So there's nothing much more we can do with this analytically. And it is a technical answer. This is technically correct. But the problem is, when we're given a function in a specific format, we usually want the answer in that similar format. The function was given without negative exponents, so we probably don't want negative exponents in the answer. So at this point, we need to bring the x back down. So that was just a move for convenience. So this is -4. The -4 stays in the top. That does not have a negative exponent. Negative in front is not a negative exponent. But we'll bring the x to the bottom, and we'll change the -5 to a 5. This is kind of like when we do a change of variables in pre-calculus, where we start out on x, we go to u, but then we have to go back to x because the original problem was in x. We give you a problem in dollars, and you do the problem in yen. I don't want the answer in yen, I want the answer in dollars. So again, it's quite often in calculus that you'll have to manipulate something to a different format and then go back to the original format for the answer for consistency. So our derivative, f prime of x, is equal to -4 over x to the 5th. Or in the other notation, the Leibniz notation, df dx is -4 over x to the 5th. And it feels like the exponent has increased by 1, but it did decrease by 1. That's because the variable's in the bottom. Variables in a bottom act very different than variables in a top. Sorry, I had to get some water. All right, so that was D. So my original D is going to be E. Let's do another problem where the notation is not good for us initially. F of x equals square root of x. Now you'll find 1 or 2 of these that are now freebies in the 1.3 or 1.4 homework using the definition with the limit. I will never throw that on a test in here. I don't plan on doing it in the homework. Like I said, I gave those as freebies as of this morning. But I will absolutely give this to you where you can apply the power rule. So scrolling back up, power rule, power rule. What's power rule? All right, if your function is x to the n, so an x with an exponent, take the exponent, drop it out front, then decrease the exponent by 1. That's it. And I'm telling you, you can use the power rule. I don't see an exponent. Mr. Beckner, you're lying to me. You can't use the power rule on that. That's a square root. Square roots aren't powers. Oh, yes, they are. Square roots are definitely powers. And this is something that we studied before pre-calculus, and we used it in pre-calculus, and we're going to continue to use it all semester in here. So this is in your exponent rules somewhere in the prereq stuff, but as a reminder, an nth root of x to the n is the same thing as x to the n over m. Do not ever forget that all semester. That's developmental math that you use in pre-calculus, that you use in calculus. If you forgot it, remind yourself of it, use it. Okay, so that's the going from radical to rational exponents. Rational meaning fractional exponents. So what we need to do is rewrite f of x. So f of x becomes, I don't see an index number right here, so what do we assume it is? Square roots are 2. So there's an imaginary 2 here that I'm only going to write for a second and remove. So that's a 2. I don't see an exponent here. What do we assume it is? It's a 1. So those are a 1 and a 2, which means when we convert that, you get x to the 1/2. The power is the numerator, the index is the denominator. Now we have this in a format we can use. So f prime of x equals, take the exponent, bring it out front, 1/2. Take the variable, leave it alone first of all as the variable, but then take the exponent and drop it by 1. So the original exponent was a 1/2, so we're subtracting 1 from it. Uh-oh, fraction math. And these are not always going to be things like a 1/2. They could be thirds, and your calculator might tell you 0.3, and that's not it. You're not going to be able to put 0.3 bar in my math lab. You've got to be able to add and subtract fractions. So this is 1/2 times x to the 1 is the same thing as 1 over 1. Getting an LCD from 2 and 1 is 2, so that's a 1/2 minus 2 over 2. Again, 1 is the same thing as any number over itself. The common denominator needed is 2, so I made it 2 over 2. I could write that 1 as 3 over 3, or 5 over 5, or 9 over 9, but that would not be convenient. Equals 1/2 x to the 1 minus 2 is -1, so the top's a -1. The denominator stays 2. So this is our answer, and it's correct analytically, but it's not even close to the format of what we originally had. It's got a negative exponent, and it's got a fraction exponent, so we got to clean that up. We got to put it back in the original format. I think it's easiest to handle the negative exponent first, so the first thing I'm going to do is say f prime of x equals 1 over now this x to the -1/2, I wrote it to the side. That's the same as counting it in the top. So that looks terrible. I'm just going to rewrite it really quickly here. That's the same thing as having 1 x to the -1/2 over 2. Those are the same thing. So we're going to bring the x from the top down to the bottom. We're going to change the sign of its exponent, so that's now a positive 1/2. Now, I didn't need the 1 in this format, but you definitely need it in this format. Otherwise, there's nothing in the top. See if I delete that. That just looks weird. So you got to make sure you have that 1 in the top. If you didn't have the 1 originally, make sure you write it at this point. Now let's change from having a fractional exponent, a rational exponent, to a radical. That's 1 over. The 2 is still in the front. But in x to the 1/2, that says you'll have a radical and an x inside. I swear the air is so dry in my house, I cough more than I do at work. Sorry for that. Humidifier might be a purchase I need with working at home. So the 1 is the power because that's the numerator. We don't need to write the 1 though. See, I don't need to write this 1. It's unnecessary, so I don't. The 2 was the denominator, so that's the index. And I don't need to write that 2 because it's assumed, so I don't. So this is the answer, well, kind of. This is analytically correct, but you can't have square roots in the bottom. So you have to rationalize the bottom. And again, this is a technique in your prereq assignments. With just a single square root like this, with no plus or minus and additional terms, all we have to do here is multiply top and bottom, that's what T and B means, by the radical. Since it's a square root. So we're going to take this 1 over 2 square root of x, and we're going to rationalize the bottom, which means to multiply top and bottom by just the square root. You can put the 2 there as well. It just means one extra step to clean up in the end. Now, if this was a different type of square root, if this was, a different type of root, a cube root, a fourth root, a fifth root, we have to clean this up a little differently. We'll talk about that another day. So distributing, the top you get square root of x, because square root of x times 1 is square root of x, in the bottom. 2, these square root of x's, you're going to multiply the insides. X times x is x squared, so that's 2 times the square root of x squared. And the square root of x squared is x. So this is the square root of x over 2x. Or you can have this as 1/2 times the square root of x over x. Both of those are acceptable formats. So f prime of x with the notations. I like the first one better personally, is square root of x over 2x, or df dx is the square root of x over 2x. So there's a decent amount going on with this problem. We had to change our radical to rational exponent form. Then we applied our power rule. You can't apply the power rule when you see square root. It's not possible. So that you do this first. Applying the power rule, oh man, we got fraction math, so you got to be able to subtract those appropriately. Then we got to make it look like it did originally. So we got to take the negative exponent, bring it to the bottom. Then we change from rational exponent to radical notation. But then we said back in pre-calc, back in introductory algebra, you're not allowed to have square roots and bottoms. So we have to rationalize this denominator. So for a square root in the bottom, that means multiply top and bottom by square root of x. This is the most popular case that you'd see. So the cleaning up was quite extensive for this. Now, what you might find in my math lab it may be okay with 1 over 2 square root of x. I have seen this go both ways. So if you get this far and you want to try that answer out, if you really, really believe that this is correct, you get 3 attempts, so you could put that in and be like, oh, that's okay. All right, cool. If it's a square root though, if you have an answer involving square roots in the bottom, I want you to clean those up on a test though. I need these rationalized because that's an important concept. You can simplify things in this format that you can't in the format with the square root in the bottom. It may even let you leave it with the negative exponent. I can't promise because I've seen a heavy amount of variability of this from program to program as well as just from problem to problem. The instructions might give you a hint as to how to answer the format, so read your instructions carefully. But if it will take the simple version, it should definitely take the version that was further down the line as well. If it doesn't, you can email me and say, hey, Mr. Beckner, I think this is right. What's going on with this? And then I can look at your problem. Okay, so I mentioned something previously, and we even saw it kind of in a special case. This thing had an extra little coefficient. What happens if there's extra coefficients? What if a term already has a coefficient? When you take the derivative, just multiply this by whatever you get. Also, you have the sum and difference rules of differentiation. It just says that you can apply the power rule to individual terms of a function separated by pluses and minuses, but not multiplying or dividing. 3 exclamation marks there. So coefficients just get multiplied by whatever you get with the power rule process. If you have multiple terms, just take the derivative of the individual terms. You apply the power rule to the individual terms. That's all it is. So in other words, before we do any official examples, if f of x is equal to 5x squared, we know the derivative of x squared is 2x. So we just take the 5 and multiply it by the 2x. The 5 just stays multiplying by the powers of everything, the x's, the numbers, all that stuff, which would be 10x. Or if f of x is equal to, let's say, x squared plus x cubed, when we did just the derivative of x squared, its derivative was 2x. When we did the derivative of x cubed, it was 3x squared. Since there's a plus sign between them, just leave a plus sign between them. That's what these last two type statements say. There's a coefficient, multiply the coefficient by whatever you get. If there's pluses and minuses, just do the terms individually. If there's products or quotients, there's a whole nother section for that, spoiler alert. So with that being said, let's get into example 2. Let me make sure I got lots of space. I don't want to end up messing anything up. Example 2, find the derivative. So I'm not even saying find f prime, I'm not saying find df dx. You can write it whichever way you want. And I also might use different letters here and there. So for our first function, we'll do f of x equals x squared minus 5x plus 12. Now, this problem should look really familiar. We did it back in 1.4 using the definition, using the limits, and that, you know, we were getting used to it at this point, I hope, if you're practicing. So we know the answer is 2x minus 5. Let's confirm it by using what we just kind of piecemealed together, with the power rule being a shortcut. Coefficients just have a multiplying effect, and sums and differences just sum and difference at the end. All right, so f prime of x. There's no square roots, there's no variables and bottoms. This is a nice, easy polynomial. So let's focus on the x squared, which says to take the exponent out front, which is a 2, leave the x, and drop its exponent by 1. And I'm going to stop showing the math on subtracting 1 unless it's negatives. And eventually I'll stop doing that as well. So we're taking the 2 and we're subtracting 1. Well, 2 minus 1 is 1. So I'll write the 1 for this step just for emphasis. Now there's a minus and a 5, so leave the minus there. And we have a 5x. Now you can still apply the power rule if you want. That's an x to the first, so you'd bring the 1 out front, you'd drop the exponent to 0, which means we don't really need to write x to the 0. So I'll show this extensively with the power rule. So we're leaving the 5 as a product, times. Now that was an x to the first. I'm going to erase it now, though. So we bring the 1 out front, times x to the 0. 1 minus 1 is 0. I'm going to pause for a second. Someone just asked about the homework. The 10 points get added, yes, at the end of the semester in my own gradebook. You will never see that reflected in my math lab. And it's going to be about 10 points. It's usually 10, but it could be 9, it could be 11, but usually 10. All right. And don't ever be sorry for interrupting. This is exactly how it would be in class. Always, please feel free to ask questions. It's nice when they're relevant, but if it's something like that, that's okay as long as it's not a frequent occurrence. Cool. All right, so again, I'm doing this the complicated way. I'll show you the short way after. Then the plus. Now that was really a 12. Again, I'll write something in here that I'm going to erase in a second. There's no x's, so you can just pretend there's an x to the 0 there because anything to the 0 is a 1. So with an x to the 0 there, we're bringing a 0 out front. So we're bringing a 0 out front. And then that's times the 12 that was already there. And then x to the 0 minus 1 is negative 1. That just seems wacky. Well, it doesn't matter because 0 times anything is 0. So this would be 2x minus 5 times 1 is 5. X to the 0 is 1. So that's just a minus 5. And then plus 0 times anything is 0. So we get 2x minus 5, which is correct. Here's the easier version. Use the special cases. So f prime of x. I'll use the power rule for the x squared. So I bring the 2 out front. I drop the exponent by 1. We'll leave the minus 5 alone. Well, hold on. I don't want to say that. This minus 5x, this term right here, just focusing on this term is linear. So if the only term there, if the only term in the function was this minus 5x, it would be a line, so the number in front of it would be the slope. Going back to the special cases, if your function is some number times x, the derivative is just the number, which goes in line with the slope of a line. So the derivative of a minus 5x is minus 5, because the slope is just the coefficient of minus 5 of a line, a linear term, an x to the first term. Then plus, going back to the special cases, this is a constant. We said under our special cases that the derivative of a constant is 0. The derivative of a constant is 0. Because constants are horizontal lines. Horizontal lines have a slope of 0. I'll draw that up after this example, in fact. And adding 0 does nothing, so this is just 2x plus 5. So f prime of x is 2x minus 5, excuse me. Minus 5, that was about to be a mistake. Or df dx equals 2x minus 5. you need to get used to using the special cases because it's going to save you a lot of time and effort. The derivative of a linear term is just the coefficient. This is a linear term, so that's why there's a -5. The derivative of a constant is 0. The derivative of a constant is 0. The derivative of a constant is 0. Pictures. Not of that specific graph. It's a little wavy. It's not my intention. In fact, let me do it better. That point right there is 1 comma a. This is a line with a slope of 1. This is f of x equals ax. And you can see that its slope is a if you use the point 0 comma 0 and 1 comma a. You'd be doing a minus 0 over 1 minus 0, which is a. So f prime is a. It's a line. Lines have the slope of the number in front of it. If you have a function that's a constant, f of x just equals a, no x, that's a horizontal line at a height of a. Horizontal lines have a slope of 0. So f prime of x is 0. So we have reasoned this both with the power rule and geometrically. Again, it is extremely important, in my opinion, to understand these shortcuts of the rules, that the derivative of a linear term is its coefficient. The derivative of a constant term is 0. It just goes away. She gone. So with that in mind, let's try another polynomial, but let's go through this one a lot quicker. And let's make it uglier at the same time. So f of x equals 3x to the 7th plus, in fact, let's just write this as y equals. Y equals 3x to the 7th plus 2x to the 5th minus 8x squared plus 9. So I did not write this in function notation. I wrote this in more of a algebraic standard y equals. It's the same thing though. It's just instead of writing f prime of x, we're going to write y prime for one of those notations. And instead of writing df over dx, we're going to write dy over dx. So again, power rule and special cases. So y prime, instead of writing f prime of x, we write y prime. Again, that looks like an exponent of a 1. That's why we really don't want to write exponents of 1s. It's a terrible idea, especially once you're in calculus. So this is not y to the first, this is the derivative of y with respect to x. So any coefficients stay, so that'll be 3 times, then apply the power rule. So bring the 7 out in front, drop its exponent by 1, and 7 minus 1 is 6. Plus, leave the coefficient of 2 out front. Apply the power rule to x to the 5th. So drop the 5 out as a product, leave your x, decrease its exponent by 1, so 5 minus 1 is 4. Minus, leave the 8. Now this x squared, take the exponent and put it in front, so that's 8 times 2. Then decrease the exponent by 1. So I'm going to write the 1 for just a hot second, but I really don't want that because it's confusing. Y prime and x, that looks like an x prime. What does that mean? So that's 2x to the first. Then plus the derivative of a constant is 0. So I'm not always going to write the plus 0 every time moving forward, but I want to for emphasis now. There was no linear term, so that special case didn't apply. So y prime is equal to 3 times 7 is 21. So that's 21x to the 6th plus 2 times 5 is 10, x to the 4th minus 8 times 2 is 16x. We do not need to write the 0. Those are not like terms. They are not combinable. And that's our answer. There might be times where factoring this would be beneficial. It's not for now, so we won't bother. Or the other notation dy over dx. See, instead of, we're not talking about f of x, we're talking about y, so that's why we don't write f prime of x or df dx. So 21 x to the 6th plus 10 x to the 4th minus 16x. Again, same answer, just different notation. With the power rule, it doesn't really matter how big the coefficients and exponents get. The basic idea is simple. If we were doing this with the definition of the derivative using limits, that's when we start hitting our lives with those big exponents. All right, let's really mix this up now. And I'm going to use a different function letter. I'm going to use g of x. You don't have to have functions be f, they can be g. So 1 over 3 square root of x, ain't nothing but a g thing, sorry, minus 6x, 6 square root of x. I'm silly, I can't help it. Plus 7 over x to the 5th. And I'm actually going to pause it there. We're going to take our 10-minute break. It's 7:56, so let's come back at 8:06 and we will pick up with this example. I can type, I swear. All right, let's get back to that example. Without being silly, I'd be insane, although I'm probably already insane anyways. I'm a math teacher after all. Muhahaha. So this is a pretty weird function. It's got a term with a square root in the bottom, it's got a term with a square root in the top, and it's got an x in the bottom with a power. All right, so all I've taught so far is the power rule in its special cases, but thankfully we've learned how to adjust. Hey, if you got an x to the fifth, bring it into the top. If you got a square root of x, change it to an x to the 1/2. If you got a square root of x, change it to an x to the 1/2, and since that's the bottom, you'll have to bring it to the top. So all of those subtle changes we did before, it's just going to be all in this problem from the beginning. So we need to clean this first. And by clean, I mean make it in a format that we can apply the power rule. So this will be 1/3 times x to the 1/2. I'm not going to sit here and spin for 5 minutes over y squared of x is x to the 1/2. We already explained that. Then minus 6 times x to the 1/2. Then a plus 7 over x to the 5th. You could go ahead and bring that to the top, but I figure I got another one I got to bring later. So let me just do the same type of step in the same instance. So that gives us our function, g of x. Let's bring things in the bottom to the top that need to be. Now the 3 can stay. So the 3 is perfectly fine in the bottom, but that x to the 1/2 is going to go to the top and become a negative 1/2. You could also write the x to the side. I'll show it both ways. Then the minus 6x to the 1/2, that was fine being up in the top already. Then plus 7, and then we'll have our x to the negative 5th. So the other way you can write this is just 1/3, and then the x to the negative 1/2 to the side, minus 6x to the 1/2, plus 7x to the negative 5. I actually prefer the second version. I think the second version is better. In my opinion, IMO in my opinion. So I'm going to go with the second version where the x's are to the side of fractions, because we're going to be bringing a fraction out front. It's just going to be easier to see that way. So g prime of x, or dg dx, I'm going to write it both ways up front. Apply the power rule. So we leave the 1/3 in the front. Coefficients stay. But then we have a times. We're bringing the exponent out front. So this negative 1/2 becomes a multiplier. Because it's negative, since I'm putting it after, I need to do it with the parentheses. You could have put it in front to avoid that. It doesn't matter if it's 1/3 times negative 1/2 or negative 1/2 times 1/3. Then we take our exponent. So here's our x. And we're going to drop it by 1. So that's negative 1/2 minus 1. I'll show that math this time because it's going to be a little more of a pain. Then we have our minus 6 times, we're going to bring the 1/2 out front. So that's 1/2. You should write it that way since the 6 is a whole, 6/1. Then we have our x to the side, and we're going to take our 1/2 and we're going to subtract it by 1. Then our plus, leave the 7, bring the negative 5 down in front or after the 7 times x to the, and then we have our negative 5 that we're going to drop by 1, and decrease by 1, that is to say. Sorry, I'm looking for something. Okay. I thought I was missing a piece of paper from later. So g prime of x is equal to 1/3 times a negative 1/2. Just go straight across. That's not an LCD situation. That's negative 1/6. Then we have x to the negative 1/2 minus 1. I'll do that to the side. Negative 1/2 minus 1 is the same thing as negative 1/2 minus 2/2, getting an LCD, which is negative 3/2. Not positive 1/2, negative 3/2. So that's here. I'll use the same color so you can see where it came from. And then the 1/2 minus 1 we did already. I'll show it one last time. 1/2 minus 1 is 1/2 minus 2 over 2, which is negative 1/2. So this will be, we have negative 6 times 1/2. That's going to be negative 3 because 2 goes into 6 3 times. And then x to the negative 1/2 time, negative 1/2. Then we have a positive 7 times a negative 5, so that's a negative 35. And then x to the negative 6. I'm not going to show that to the side. Now for this problem, let's just focus on getting rid of these negative exponents. Let's bring these all to the bottom. So that 6 was in the bottom, so we'll go negative 1 over 6, x to the positive 3/2 now. The negative became a positive. The 6 did not move positions though. Minus, this 3 is in the top and stays in the top. The x is what has the negative exponent, so that gets brought down, and we make it a positive 1/2. Then minus, the 35 stays in the top. The 35 is not what has the negative exponent. Now, let me show you something different here. If there was a parentheses around this, and that's what had the negative exponent, then the 35 would come down. But it doesn't, so it doesn't. Just the x to the positive 6th. Then we can change to our radical notation. So this is going to be negative 1 over 6 times the cubed root of x squared minus 3 over the square root of x minus 35 over x to the 6th. Now this one's got a little bit more beef to it. So I typically on a test would not have you rationalize this one, especially because of the second one. Like I said, if you have a problem that only has a square root in the bottom, that's when I expect rationalization. Here, it's a little different, so let's just call that our answer. G prime of x, aka dg dx. I don't want to have to write that whole string twice. No matter which one you use, it's equal to negative 1 over 6 times the cube root of x squared minus 3 over the square root of x minus 35 over x to the 6th. Again, it looks a little weird because I just didn't want to write that twice. Whether you use g prime equals or whether you use dg dx equals. Not df, not f prime, because the original function was g. Be consistent with the letters. Okay. So before we do this marginal stuff, let's do another example, whole new set of examples. So this is example 3. And let's go back to finding tangent lines. So for example 3, we are going to find the equation of a tangent line to the function f of x equals, well, I don't know, x cubed minus 4x squared plus 10 at x equals 3. Find the equation of a tangent line for the function x cubed minus 4x squared plus 10 at x equals 3. Okay, but we don't need to use the definition of the derivative. We don't need to use the limit stuff. This would be a much longer problem. We can use our power rule now. I love these types of problems. One of my favorite introductory calculus problems, especially now that you got your power rule and you can do these a lot quicker. So what do we need? We need a point and a slope. We were given half a point. This x equals 3, that's half of a point. It's the x coordinate. What's the y coordinate? Find the y coordinate by plugging it in. So f of 3 would be 3 cubed minus 4 times 3 squared plus 10. which is 27 minus 4 times 9 plus 10 PEMDAS. That's 27 minus 36 plus 10. Notice I did not take 4 times 3 first and then square it. 27 minus 36 is negative 9. Negative 9 plus 10 is positive 1. So the point is 3, 1. Now we need the slope. To get the slope, we need the derivative. To get the derivative, we're using the power rule now. So f prime of x, or df dx, whichever notation you like. For x cubed, drop the 3 out in front, leave the x, then decrease its exponent by 1. 3 minus 1 is 2. For the minus 4x squared, leave the minus 4 times. For the x squared bit, take the 2 and drop it out front. Then subtract 1 from its exponent. 2 minus 1 is 1. And again, I don't really like writing that 1, so I'm going to erase it. Then a plus. The derivative of 10, the derivative of a constant. The derivative of a constant. That was 0. That was one of the special cases. So cleaning this up, f prime of x is equal to 3x squared minus 8x. So that's the function that governs the slope, the rate of change at every single point. Now we can find the slope at the particular point we're interested in, which was 3. So we do f prime of 3. So that would be 3 times 3 squared minus 8 times 3. Well, 3 squared is 9, so that's 3 times 9 minus 8 times 3, which is 27 minus 24, which is 3. That is our m. Now that we have our slope and our point, we just plug those into, for the 30th time, y minus y1 equals m times x minus x1, and solve it for y. So our line becomes y minus 1, that's the y1, the 3 is the x1, equals the m, which is 3, as we just found, times x minus, and the x value was 3. Just a coincidence that there are 2 3s here. This first 3 was the slope. The minus 3, that was the x1, the coordinate. That was the given 3, in fact. Well, we can clean this up. I'm just going to use a little arrow to say, hey, we're going over here. That's y minus 1 equals 3x minus 9. I'll show the algebra. Add 1 to both sides. And that gives us y equals 3x, negative 9 plus 1. Negative 9 plus 1. How do we handle that? Different signs, subtract, keep the sign of the larger. 9 minus 1 is 8. Sign of the larger is negative, so negative 8. There is our equation of a line. Okie dokie. So that's what they asked for. That's what I asked for. Now, this function is not going to be super fun to graph. You did learn back in pre-calc 1 how to graph the general polynomial, as long as it was factorable, as long as you could find roots, and then doing that synthetic division stuff. And then you could graph the function, you could graph this line, and you could show that it's touch and go at x equals 3. We're going to skip the detailed analysis of graphing the function and just pull out a TI-83. Hello, Mr. TI-83. How are you doing? That was for another class from this morning. So what I'm going to do is I'm going to graph the function x cubed minus 4x squared plus 10. Let's just see what this looks like by itself. Pretty standard looking polynomial. This looks like it hits the x-axis over there at about -1. Let's see. Yeah, a little high. How about -1.2? Still a little high. How about -1.8? Nope. How about -1.6? So I'm gonna have a hard time telling where it actually crosses 0. So that's why I'm not asking us to do that. Either way, the point is, here's the graph. Now we want to see the tangent line at x equals 3, and we said it's supposed to be this, 3x minus 8. So if that's true, when I go and put a second equation in, here's the 3 about there, you should see a line touch and go right there, y equals. Let's go down to the other one, 3x minus 8. Now what I'm going to do is, I'm going to turn the first one off for a second so you can just see that it's by itself. So I go to the equals, and I hit enter. Now it's going to graph the line, but not the curve. So there's our tangent line, just so we can see where it is before everything's all together. Now let's put them together. So turn both on and graph. Now this is supposed to touch and go at x equals 3, trace. If I type 3, hit enter, that looks like the line and the curve are intersecting there, but it's kind of pulled back. So let me zoom in a little bit. Let me just make I'm going to pick a window of my choice. I'm going to go from an x minimum of, let's say, 1 to 5. And let's do a y minimum of, the height of that point was 1. So that should be pretty good if I just do the 1 to 5 as well. Let me actually go 0 to 4 on the y's. 0, just so it's centered a little more. That's a little nicer. If I hit trace and I type 3, now it's a little easier to see. There's our tangent point. So it's intersecting the curve one time only in that region, not 2 times. That would be a secant line. And you can see that the slope of that line seems to be matching the steepness of the curve at that point. So if I wanted to do this at x equals 4, I would have to find the new point. What do I get when I plug in x equals 4? Give me a new function value. Then I have to plug the 4 into the slope formula, the derivative, which was here, and get the other slope, and then go through the equation again, because there are infinitely many tangent lines to this thing. It's just a matter of where you want to be at. But that's how our graph looks. Here's our curve, here's our tangent line. You can see the touch and go demonstrated. Let's do another one for this. So we'll call that 3a. For b, let's do the same function, but at x equals, let me pull up the graph and see where I want it to be roughly. We'll do 2. We'll do it at x equals 2. So our function is still x cubed minus 4x squared plus 10. Our derivative is still 3x squared minus 8x, but now we're plugging in x equals 2. So f of 2, to get our point, would be 2 cubed minus 4 times 2 squared plus 10, which is 8 minus 2 squared is 4, 4 times 4 is 16, plus 10. 8 minus 16 is -8, -8 plus 10 is 2. So our point is 2, 2. We can confirm that with the calculator. I just type 2 and hit enter. Yep, there we go, height of 2. Let's find the f prime of 2. So that would be, remember our derivative is here, the 3x squared minus 8x. So that's 3 times 2 squared minus 8 times 2. 2 squared is 4, 3 times 4 is 12, minus 8 times 2 is 16, and 12 minus 16 is -4. So that's our slope. And if you look at this curve right here at this point, We're going down in that region, so the slope of that tangent line should be negative. These things are making sense. This is a positive slope. This one should be negative. So our line, y minus the y1, which is 2, equals the m, which is -4, times x minus the x1, which was also 2. Again, here's our x1 and y1. This was our m. Clean this up. That's y minus 2 equals -4 times x plus 8. Just watch your signs. Why did I have a parenthesis still there? That's my bad. -4x plus 8. I'm trying to rush. Add 2 to both sides. You get y equals -4x plus 10. Again, if you don't have to show this little detail, nobody's going to care in calculus. So here's our line. Now I'm going to put that one on our graph as well, and I'll leave the first one up because they shouldn't really be interacting. So let's go -4x plus 10, and go to graph. And there it is. If I hit trace, -4. Sorry, not -4, 2. That is exactly where the line is touching the curve. And it's kind of blending up here a little more, but it is just touching and going. It's touching once and once only in that region. Now, what's fun is there is an app online called Desmos, and they've got a really cool program that you can kind of see this with. You can see this demonstrated. You can freely move your x value, and you can freely see the tangent changing. And I don't remember that website off the top of my head. I have it written down in my notes somewhere, which was that page I was looking for, I mentioned. It just must be in another folder. So I might demonstrate that at the beginning of next class, how you can just see this tangent line move along the curve as you go. Maybe I can do it now. Desmos derivative demonstration. All right. So that function was wrong thing. X cubed minus 4x squared plus 10. X cubed minus 4x squared. X cubed minus 4x squared plus 10. Let me confirm that that's right. X cubed minus 4x squared plus 10. Okay. Then the derivative, they have this is not exactly the same as the link I have, but that's okay. G of x, a, there we go. All right, so let me pull this out some, move the window. So all I did was I typed the function, and it automatically gives us the derivative. We don't have to type it in this version. I like the version where you have to. They even show the equation of a tangent line in its analytic form without writing what there's function values here. So this is the g of a, the slope, and this is the function value at a. Anyways, point being, there's the same graph that we had in our TI 83, and the red line is the tangent line. So I can slide this, and you can see it freely moving from x value to x value. There's like a little dot that's moving up and down. I don't know what's up with that. It is what it is. Just focusing on the red line. So that red line is dictating the slope as you move along the function. So as I get closer and closer to this peak, that red line goes completely horizontal. So at that peak, the slope is 0. That's what a tangent line would look like there. On the left side, you've got positive lines, but the closer you get to that peak, the flatter the tangent line gets. And it gets really flat really quick, as you can see. And then as you go to the right side, your tangent line is now pointing down, and it gets pretty steep for a bit. But then as you get closer to that valley, it starts coming back up until it hits completely horizontal somewhere in that ballpark, which is hard for me to hit on my mouse. But somewhere in there, it's completely horizontal between here and here. And then it just gets steeper and steeper and steeper and steeper as you move right along the function. So this right here is a great website. As you can see, all I did was I just Googled Desmos derivative something, and it took us to this website. What did I Google? Desmos derivative demonstration, and then it was the tangent line and derivatives. So if I had Googled tangent line and derivative, that would have probably been the first option. So play around with that. So you can make your function whatever you want. So here, this is some crazy trig function. If this was regular calculus, we would study trig functions, and it would be even more formulas for us to memorize. We only get, maybe a dozen or 2 dozen formulas in here to memorize throughout the semester. Regular calculus, they get 50 or 60. So be thankful you're in an applied class, because we don't do anything with trigonometry because you didn't have pre-calc 2. But this blue curve is this sine of x plus 0.3x, whatever that has to do with. And if I click the dot and hold it as I drag it, you can see the tangent line moving along the curve, and it goes up because its slope is increasing, and then it starts decreasing until it's 0, and then it's negative, and then it goes back to positive, and then it starts flattening again, and then goes back to negative. And sine functions do this infinitely. So it's like riding a wave. So if this little purple dot was a boat, and the blue was the ocean waves it was going across over time, that red line would demonstrate your view, your perspective along the water. And it's this type of thing that causes seasickness, because you're looking at the sky, and then you're looking at the water, and then you're looking at the sky, and you're looking at the water, and blah! There goes lunch. So when you talk about things like pitch and yaw and whatever, it just leads to throwing up. That's basically the idea right there. It's some very simple calculus, because waves in an ocean can be modeled with trigonometric functions, and your perspective can be modeled with a tangent line at a point along those trigonometric functions. This one just happens to be growing over time, so this wave is getting higher and higher, but we don't have to worry about what that really means. Just a normal sine wave without that additional term. This is more like a real ocean wave. Oops, I need to grab my dot. And make sure you're grabbing the dot on the curve. That's how you actually move things around. If I just grab somewhere else, it moves the graph. If I grab the red dot, it has the same effect, but I like to grab the dot on the function. All right, cool. So fun little website. Back to the notes. Last thing for the day. I don't really feel the need to get into 2.4. I'm not 2.4, I'm sorry. My notes are based on an old textbook, the section titles. Same material, just different titles. Their chapter 2 is our chapter 1. Where am I? Marginal analysis. Not margarine analysis, marginal analysis. This is something we'll get into, not necessarily in this section, but we will talk about here and there, peppered throughout the rest of the semester. The word marginal means derivative. It means, i.e., marginal means the study of the change of a function, generally financial topics. Marginal means derivative. So when you want a marginal revenue or a marginal profit or a marginal cost, actually, let me do it in the same order I have to be consistent. Cost, revenue, profit. So marginal cost or marginal revenue or marginal profit, there's 3 main ones that we talk about, is the cost, revenue, profit associated with producing or selling 1 more unit. In fact, The one more units, I want to have all caps and underlined and exclamation marked. So you're a company and right now it's costing you $10,000 to produce 50 units. It costs you $10,000 to produce 50 units. And your boss comes to you and he says, well, how much is it going to cost us to make one more unit? That would be the marginal cost. Now, it's not $10,000. That was the cost to make all 50 units. And costs are not necessarily a linear trend. That $50,000, I'm sorry, what the heck number did I say? I think I said $50,000. I don't remember. All right, so let me start fresh. Let's say our cost, no, I remember what I said. Our cost to produce 50 units was $1,000. So say the cost to produce 50 units is $1,000. Boss asks, what is the marginal cost at this point? He is asking how much, I'll get rid of the underline in a second, does it cost the company to make one more unit? So how much does it cost to make the 51st unit? That's what's being asked here. The marginal cost at 50 units is the cost to produce the 51st unit, or the marginal revenue or the marginal profit. All three of those words are interchangeable. And if you don't know how to calculate profit based on cost and revenue, we'll lay that out in just a second. But again, these are generally associated with derivatives. So if you have a function, you take its derivative, and if you want to know how much does it cost to produce the 51st unit, you plug in the 50th unit. So if you want the cost for the 51st unit, you plug 50 into the derivative. Now, I can't tell you what the 51st unit costs here is because I don't have a function dictating the cost. I just gave you a number. This problem is not solvable as it is. You might think, oh, okay, we'll take 1,000 divided by 50, and you get 20. So it's 20 per unit, so the next one's 20. Not necessarily. Again, maybe your rent is $900. Your rent doesn't go up when you make that 51st unit. Your rent doesn't go up when you make that 1,000th unit. Your rent doesn't go up when you make your 10,000th unit. The rent's still $900 every month. What changes is production costs, materials, paying employees, things like that. So maybe you have a fixed cost and you have a variable cost. That's a pretty common model. A common cost model is one that only considers fixed cost, i.e. constant, and variable cost, i.e. changes per unit. Now, does this have to be the model? No. We can give you any type of polynomial or radical or rational equation we want to for a cost. I'm just saying that this is pretty common for an introductory model. Now, I say introductory because you have what are known as growing pains with companies. You know, when you're going from making 100 units to 200 units to maybe even 1,000 units, maybe it just costs you an extra 5 cents each time. But all of a sudden, maybe you want to make 100,000 units and you can't do that in your current factory because there's not enough time in the day, there's not enough employees, so you got to buy another factory, you got to hire more people, you got to have more space. And even just hiring more people in the same space, you can get clustered and run into each other, and that can affect how much you produce, or people start talking to each other too much, something like that. So costs are not always just a linear fixed and variable model, but it's a good starting point a lot of the times that we'll see. Cost, we generally denote as C of X. Revenue, we generally denote as R of X. And then profit, We generally denote as, you might guess it, P of X. Cost is money in, revenue is money out. Profit is the difference of the two. So profit, P of X, is actually a formula which you should have memorized. It's simple. It's revenue minus cost, money out. I wrote out and in backwards, obviously. Cost is money out. Revenue is money in. Please forgive me for that. So profit is money in minus money out. So that's revenue minus cost. So our cost is C of X, our revenue is R of X, our profit is P of X. Costs and revenue are functions that are typically given to us, or they'll tell us it's a standard linear model in which we can build. And if you can't build a linear model, that scares me because you should have done that in pre-calc 1. Profit is just the difference of revenue and cost. Profit is the difference of revenue and cost, of course, in the correct order. So the marginals, marginal cost is C prime of X. And again, that's that curly looking comma. We usually don't make them curly looking when we do it. It's just a straight line. So please associate that correctly. Marginal revenue is R prime of X. And then marginal profit is P prime of X. Again, not margarine profit. We're not making money off butter. We could have a marginal margarine profit. Say that 5 times fast without laughing. So again, this is something that we'll study kind of in and out throughout the semester. We might do a problem later in chapter 1, might do some problems later in chapter 2, might do some problems in chapter 3. This is one of my favorite topics in this course. I also really like the idea of elasticity with economics. And if we have time, we'll get into it, but I highly doubt that we will. But elasticity of supply and demand kind of helps you figure out where you should be producing and how, if you produce more or less units, what happens? Do you make more money? Do you make less money? Because a lot of people just say, oh, we'll produce at the equilibrium point. Yeah, that's a great start, but sometimes you need to get a little more in depth with things. So you start going into your marginals, you start going into, as I said, elasticity, which has everything to do with marginals. But for all right, just going to transfer again. Just give me a minute. We finished with 1.5 last class, which was on the very, very, very beginnings, the introductory simpler rules of doing a derivative. So we had the definition based on the limit where we said that the limit as h goes to 0 of f of x plus h minus f of x all over h, we called that the derivative. We called that f prime. It gave us the instantaneous rate of change. We called it a derivative. And this was the definition based on a limit. Then we introduced the power rule. We said that if your function was of a specific format, if it was a polynomial with just your general x to the n term, that the derivative, f prime of x, you took the exponent, you brought it out front, you left the x there, and then you dropped the exponent by minus 1. We also had special cases where, like, if your function was a constant, the derivative was 0, or if your function was just linear, So a number times a variable to the first power, then the derivative was just the coefficient. And we related those geometrically as well as algebraically as to why they work. And we also showed with the power rule that it worked too. Now, we also said that if you had sums and differences, that you could just take the derivatives of sums and differences on their own. I'm going to start typing now because this is where we're getting into the new stuff. So the derivative of a sum or difference is just the derivative, it's just the sum or difference of the derivative of each term. And the clacking on the keyboard might be a little louder now from the mic, so hopefully that's not an issue. This is something, again, in chat, let me know, and we can adjust from there. I don't like having these notes pre-typed necessarily, but if I absolutely have to, I will. But I kind of like going at your speed. So the derivative of sum or difference is just the sum or difference of a derivative. In other words, having pluses and minuses of extra terms really doesn't have a drastic effect. But we did point out that this is not true for products or quotients. Let's see what someone said. How far will we know in advance? So we had said on the first day that tests will always be announced with a minimum of 1 week prior to the test. So, and I will always have, unless there's a special exception, when we finish the material for a test, the test will be 1 week later. So if I know, say 3 classes in advance, I know the next class I'm going to finish the material for a test, then I'll say, hey, in 3 classes we're having a test. But the absolute worst case scenario is maybe I'm not sure if we'll finish a section or not, so I just hold off on saying that. And then when we do finish it, I'll say, all right, that's the end of the chapter. The next test is going to be just on this chapter. So that means our test is in a week. So again, the main flow is we finish material and then a week later we have our test. And the test is not just going to be on one day. You'll have a couple of days to get it done. I'm thinking 2, maybe 3 days, depending on when we assign the test, whether it's over a weekend or during the regular week. So you'll have a couple of days to get this done because I know, not everyone has the same situation. Some of us might be sitting in our cars next to the TCC parking lot to get our internet. I don't know. So I don't want to have just a designated hour and a half for testing. You'll have some time. There will be reviews, and as we get closer to the end of chapter 1, which the first test will be on chapter 1, then we'll start spitting out some more details about it, whether the review will be emailed to you or whether it'll be in my math lab, whether the test will be its own paper document or whether it'll be my math lab test, because I'm going to kind of mix and match things as we go. So good question. But for now, let's get back into 1.6. Product and quotient rules. Product and quotient rules. Oops, wrong button. 1.6, the product and quotient rules. I feel like I set up the title of this section perfectly by saying, hey, our power rule, it's really nice and quick. It's got some special cases, and it even works really well with pluses and minuses of different terms. I've mentioned that it doesn't work for products or quotients, so there must be a rule that goes with those, and there most certainly is. So let's say that given, or underline, given a function expressed as a product, let's say that product is f of x times g of x. That little star means times. I don't even have to have the star there. If I do this, that still means the same thing, but I want to be emphatic. You could just do a little dot. I would not want to use the x as a multiplier in a calculus class ever. That's just a bad idea. A business calculus class, at least I should say. If we're going into multivariable calculus and doing cross products, that's another story. So if your function, I'm not saying the function is f of x. I'm not saying the function is g of x. I'm saying the function, I'm going to think about it as a product of one thing and another thing. So I'm thinking about the function as a product of two functions, kind of. So given the function expressed this way, its derivative would be. So I'm going to write this out in hand. So d dx, the derivative of something written as a product. So again, the thing inside the bracket here was our original function, and I'm saying to take the derivative of it. So we're using that Leibniz notation. I don't want to use f prime because I'm saying f is one of the insides to this. Same thing for g. I could call this function h of x, but then it's just too many letters. So the way this works, and it's another case of we're not going to do the derivation. This is not a derivation class in general. We'll do that sometimes, but very rarely. It's f prime times g of x plus f times g prime of x. In other words, if you wanted to use your words, the derivative of a product is the derivative of the first times, so let me say the derivative of the first function times the second function plus the first function times the derivative of the second function. That's using our words. Each of these terms has something about the first and the second function, fg, fg. In the first term, it's the first part of the product that has a derivative, but the second one does not. In the second term of this, the first part of the product now does not have a derivative, but the second one does. So it's a mix and match. Think of this as a mix and match. Each of these terms has to have something from both parts of the product, where one of them's the derivative and the other's not. Now, honestly, there are a ton of ways that you can rearrange this formula, and this is a formula that you have to memorize. This is known as the product rule. We will use it over and over and over and over and over. So you had better memorize this yesterday, and I'm saying that exaggeratively, but as soon as possible. So this is a little bit more than just the power rule, and most of the time these f's and g's are going to be polynomials, so when you actually go to do this f prime of x and g prime of x, you'll be doing the power rule to get those. Now, something I've mentioned before, and I will still mention every now and then, we are going to be doing derivatives of a very limited set of class of functions. We stick to polynomials and rationals and radicals almost exclusively. We don't do anything with trigonometry, so sines, cosines, and tangents. In a regular calculus class, we'd be doing derivatives of those. We'd have formulas for those. The analytics of them are much more complicated and complex, and those are two different words and meanings. We'll get into exponentials and logarithms eventually in here, but we only do a couple of the types of those, whereas in a regular class we do all of the types, so which that means more formulas. Again, the point of this conversation being we really don't have to memorize but maybe 25% of the formulas of a true calculus class. So I don't really like to ever hear people complaining, oh, I've got to memorize all these formulas. And I know that, hey, you're not in a real calculus class, so your complaint might feel validated. But again, imagine if this was the real calculus and we had 4 times as many formulas, all of which are more complicated than what we get. So just take that as a grain of salt, is all I'm saying. So what's the variability to this? How can you play around with this? You don't have to have the first term have the f prime. The second term could have the g prime, and the first one could have the f prime. You don't have to use the function notation. So here's a shorthand version of this. D dx, without showing the variable dependency, f times g, this would be f prime g plus f g prime. Or you could have this. I'm just going to use a different color to say it's the same thing. The prime orders don't matter. I could do f g prime plus f prime g.
Or the order of the f's and the g's don't matter. I could do g then f prime plus g prime then f. Or I can do g first in one and f first in the other. I could do f times g prime plus g times f prime equals, the list goes on and on and on because of the different properties of addition, the commutative property, the associative property. You can swap the order of products and it doesn't matter. You can swap the orders of sums and it doesn't matter. So I'm not going to write this rule 50 times every time, and you can do it any of these 1, 2, 3, 4, 5 different ways I have, plus any of the others that actually work as well. So there's like 16 different ways you can get this right ultimately. But as long as you have a way that works with you consistently. Instead of saying f and g, what I tend to say is first and second. So instead of saying f, I'll say first. So that's the derivative of the first times the second plus the regular first times the derivative of the second. So this is kind of how I'll talk things out typically. I'll say first and second instead of f and g. So these little 1 exponents, we should know by now these are meant to be primes. That really is one of the major reasons that we say don't ever write exponents of 1, because when you get to calculus, an exponent that's 1 kind of looks like a prime, which looks like a derivative. So let's try this out. Let's stop rambling. Let's not talk about it. Let's be about it. Example 1, and we're going to find the derivative using the product rule. A, and we're going to start out with something simple. F of x equals x cubed times x squared. Now this f is not the same f and g from before. I'm saying the function is f of x. Before I was using f and g to denote a first and a second part of a product. So the x cubed is kind of like the f of x in the rule itself, but again, I'm not going to call it f and g. I much prefer just to call these things first and second. So I'd call the x cubed the first and the x squared the second. That's a product. So the f prime of x would be, we're going to take the derivative of the first times the second. And I will admit, this is not my preferred order, but it's how I start things out because that's the way the textbook does it. But I do have a better order, in my opinion, that I'll emphasize sooner than later. So we're going to go the derivative of the first times the second plus, and then flip-flop, first times the derivative of the second. Now each of these is a power rule. So maybe we want to go ahead and lay things out as to what they are. If you want to show what the derivative of the first is and what the derivative of the second is, that's not the worst idea in the world. So if the first thing is x cubed, its derivative, these are all just power rules. Bring the power down, drop its exponent by 1. So that would be 3 times x to the second power. You should all have that power rule memorized absolutely already. If you don't, it is going to do nothing but hurt you. If you spent 5 days over the weekend without putting any hours into math, that terrifies me. The second function is x squared, so we're going to take its exponent and put it down in front, so the 2. We leave the x alone, but then we decrease its exponent by 1. 2 minus 1 is 1. I'll write the 1, but I'm going to write it using the fancy 1, so you can really see that it's not a prime. But again, I'm not going to write that x to the first anymore from now on. So going based above, the derivative of the first times the second. So you're just doing a mix and match. One time you use the regular, then the derivative. So the derivative of the first is this. That's the 3x squared. That's the derivative of the first. And I'll do the derivatives in red and the non-derivatives in black. So then times the second function times the g of what I'd call g of x. The second was the x squared. See, one of them is a derivative, the other is not. That's what's important. Then we have a plus. That's our plus symbol separating them. And then we just do a first and a second again, but because we used the derivative of the first last time, we'll do the derivative of the second this time. So we're going to use the regular old first function, was the x cubed, times. Then we'll do the derivative of the second function, which the derivative of the second was the 2x. So again, the reds were derivatives, the blacks were not. But this is able to be cleaned up, so we should absolutely clean this up. I'm just going to stick to black now. So 3x squared times x squared, that's 3x to the fourth, and plus x cubed times 2x. Well, x cubed times x is x to the fourth, so that's 2x to the fourth. And what we end up here with is something that has like terms, x to the fourth, so we add the numbers in front. 3 plus 2 is 5. So we get 5x to the fourth. So our final answer, f prime of x, is 5 times x to the fourth. Now, maybe you don't trust this. Do you trust this? I didn't prove the formula. I just said, here it is. Here's the product rule. Jump off the cliff with me with a leap of faith, metaphorically speaking, not literally. Trust me. Well, one of the best things you can do when you're given a formula, if you don't trust, is try and rearrange the original function into something you would have known how to use before the formula, do the derivative that way, and see if you get the same answer. So what I'm going to do now is an alternate approach. So that f of x, which was x cubed times x squared, I hope that every single one of you knows that that could have just been written as x to the fifth. So our function is really just x to the fifth, which means we can take the derivative super simply just by using the power rule. It's a single term, so there's no product anymore. We can just do the power rule. Drop the 5 out front, leave the x, but decrease its exponent by 1. 5 minus 1 is 4, and it's the same answer. So yes, that product rule did work. So what you might be thinking is, all right, Mr. Beckner, if it's so much quicker to do it by multiplying ahead of time and then the derivative, why would you take the derivative and then clean up afterwards? Why would you have ever done it the way the black and red ink lays out instead of just do it the blue every time? Because guess what? Your original functions that you have to take a derivative of are not always that simple. It's not always just x cubed times x squared. Usually, it's something like x plus 3 times x minus 7, or 5x to the third plus 7x squared minus 12x plus 3 times, and then something equally as long. And doing that product before the derivative might be more time-consuming then. Or maybe you don't even know how to do that product, but if you have the product rule, you can at least take the derivative and get something analytically correct. So that is the reason we have the product rule, because usually our functions are not this simple. Me, personally, your teacher, if I had this function as a homework problem, x cubed times x squared, and I wasn't told to use the product rule, I would have done it the blue way. So let's see another one. Let's step up the difficulty just a touch. B. Let's have our function, whether it says f of x equals or y equals or whatever, and you don't even have to write it as a function. I can just write the polynomial terms. Let's have 2x plus 3 in parentheses times x cubed minus 2. That's x cubed minus 2. So yes, admittedly, if you wanted to do the derivative of this, you could FOIL it out first. So take the 2x times the x cubed, et cetera, et cetera, et cetera. Then you could just do a derivative and it would all be regular old power rules. But maybe you don't want to FOIL, you want to go ahead and do your derivative and then deal with the rest of the math later. Or maybe it's a much worse product and you'd rather go ahead and do the derivative now. So let's again identify what the first and the second things are. The first is this parentheses, the 2x plus 3. That's what I call first, and then I'll call the x cubed minus 2 the second. If you want to call them like a y and a z, or an a and a b, or give them some letters, that's fine. but I like using first and second. So the derivative of the first, we're just considering the first parentheses now, 2x plus 3. So the derivative of the first. All right, the derivative of 2x, this was one of those special cases. I'll scroll up to a -1 last time. The derivative of a linear term, just a number times a variable, is the coefficient, because the derivative of a line is its slope, and the slope is the coefficient. So the derivative of 2x is just 2. Then the plus 3, the derivative of a constant, scrolling up again, the derivative of a constant is 0. And again, we've rationalized this all algebraically and geometrically last time. The derivative of a constant is 0. So if you feel the need to write a plus 0 here, you can, but I'm not going to do that anymore. The derivative of the 2x was the 2. The derivative of the 3 is nothing, and I'm not going to write nothing. That's a lot of negatives, not nothing. All right, well, how about the derivative of the second function? That's our x cubed minus 2. So for the x cubed, we bring the 3 out front. We write our x, and then we decrease the exponent by 1. So the derivative of x cubed is 3x squared. Then there's a minus and a 2. But the derivative of a constant, the derivative of 2, is nothing. So I don't need to write a plus 0 here. All of that would be unnecessary. I'm just going to do this. So the derivative of the first is just 2. The derivative of the second is the 3x squared. So with that, we're able to get our f prime of x, the derivative of the original function. So again, it goes in the particular order I'm using for now. And again, not the order I like ultimately. I'll change this order a little bit later, but it really doesn't matter because there's like 8, maybe 16 different ways you can write it, and all of them are right. So I'm going to go the derivative of the first times the second. And the derivative I'll do in red ink. So the derivative of the first was this 2 times. Then the second function was the x cubed minus 2. Where's that circle still there? There we go. Black. So the second function was the x cubed minus 2. Again, this is the derivative of the first times the second. There we go, plus. Now, since we used the derivative of the first last time, let's use the regular first this time, which was the 2x plus 3. And you definitely need lots of parentheses for this stuff, especially for binomials and trinomials. Then times. Now, last time we used the regular second function, so we're going to use the derivative of the second function, which is the 3x squared. Again, derivative of the first, second, plus first, derivative of the second. It's a mix and match. None of these terms has both derivatives. None of these terms has both regular functions. Each term has an f and a g, or a first and a second, so to say. And now we just need to clean this up. With the first part, we got a 2 that we can distribute. So f prime of x is equal to 2x cubed minus 4. Then for the second part, we have a 3x squared that we can distribute. We can give the 3x squared to the 2x and then to 3. So 3x squared times the 2x is a plus 6x cubed. Watch your signs for everything, of course. Then a plus. 3 times 3x squared is a 9x squared. And then if you have any like terms, you combine them. 2x cubed, 6x cubed, that makes an 8x cubed. Then we have a 9x squared, so plus 9x squared, then the minus 4. So f prime of x is equal to 8x cubed plus 9x squared minus 4. That's the derivative of the original function. I'll do the trust fall, if you want to call it that, one more time and only one more time. So do you trust this? Because it gets much worse to do this trusting issue after this part. So we're going to get to more complicated ones. So let's take the original function and let's FOIL it out. Before we do any of this derivative stuff, let's FOIL out the original function. So the 2x times the x cubed would give us 2x to the fourth. Again, that was the 2x times the x cubed. Then the 2x times the negative 2 is a negative 4x. So we've distributed the 2x. We're done with that guy. Now let's distribute the 3. The 3 times the x cubed, that's the inner. We did the first and the outer. So that's going to be, and I don't want to leave that blue cross out. So 3 times x cubed is a plus 3x cubed. Then 3 times negative 2 is a negative 6. So if you take the derivative of this, which is just a straight up power rule, there's no products anymore. The derivative of the 2x to the fourth, remember constant coefficients just stay out front, so you leave your 2 out front. So 2 times. Bring the 4 down, then decrease its exponent by 1. So again, the 2 stayed, 4 got brought down, and then its exponent dropped to a 3. Then we have a minus 4x. There's no exponent with this term, so that's one of the special cases. The derivative is just the coefficient. It's not 0, it's negative 4. Then we have this 3x cubed, so plus, leave the original 3 out front, so the 3 I've written here is this one. Then bring the exponent down, which is also a 3, coincidentally. Decrease the exponent by 1, so that's x to the second. Then we have this minus 6 at the end, but the derivative of a constant is 0. So the derivative of the minus 6 is a plus 0 that I'm not going to write. I'm going to erase it. Well, guess what happens when you clean this up? You get f prime of x is equal to 2 times 4 is 8, so that's 8x cubed. The minus 4 stays, then a plus 9x squared. And you know what? There's nothing necessarily wrong with the order of these, but we generally like things in descending order when we can make that happen, which is 8x cubed plus 9x squared minus 4, which is the same thing we got originally. So I hope that that's enough for you to trust this product rule by now. If you don't, you can continue to show the work both ways, but I can guarantee that this is going to get much, much uglier. All right, so let's try another one. We got a couple more up our sleeve. And I'm actually going to swap the order of C and D that I usually do. Not that you care. And I'm going to write this as y instead. Y equals parentheses x to the fourth plus x squared plus 1 times x cubed minus x. So yeah, you could take this trinomial and multiply it by a binomial. You'll have 6 products to do. And it's kind of a nuisance. Maybe it would be easier to do the product rule and then deal with what you have after the fact. Maybe I'm lying, maybe I'm not. There's variability here. Sometimes it is actually easier to do it one way versus the other. And guess what? I guess how you figure out which one's quicker? Practice. So you learn, hey, I should do this type. I should go ahead and multiply this type quicker. I'm sorry, I should multiply this type first because it's quicker. And then you'll say, all right, this type that I've done 100 times, I know that I should do the product rule first, then multiply everything out because it's quicker. But if you only do this 3 or 4 or 5 times, you're not going to learn those efficiencies, which is why I say, even though we only have typically 10 to 20 homework problems, do problems over and over and over. Go to your online textbook, go to the homework section because there's way more homework problems listed there. Go to the internet, find things that are similar so that you have more practice. I wish that the homework wasn't departmental and that I could just give you like 100 problems and say, hey, do this. But then I'd look way more mean than the rest of the teachers. But unfortunately, my students would be more proficient. So it's a give and take.
And actually, just like last time, I wanted to leave you today having seen the example, give you an opportunity to maybe try it on your own over the next week before next class. And then you can compare your results with what we do when we start back. We will do this example with the product rule, the same way that we just did A and B. And like I said, if you did it on your own, you'll be able to compare your results. But as your friendly reminder, we did finish 1.4 super early in the evening, and we finished 1.5 just a little bit ago. So those homeworks will be due on the 7th. When we come back next time, we will, of course, finish 1.6. And I'm trying to think off the top of my head if we'll finish 1.7 or not. We'll obviously get into it. I'm not going to make any promises right now. I haven't gotten that far ahead yet. So as always, if you have any questions, email me. Make sure you're keeping up with this homework. Make sure you got 1.1 through 1.3 due over the next couple of hours. If you haven't already, you can sprint to the finish. And then if you're sprinting now, maybe start working on 1.4 and 1.5 sooner so you don't have to sprint next time as well. All right, I hope this was helpful. I hope this was informative. We'll be back doing the same thing next Monday. Well, new stuff, same time. So have a good one.